Hello everybody, and welcome back to another Big Ideas lesson. Today for our Algebra 2 lessons, we are talking about section 1.2. Last class, we spent quite a bit of time talking about different parent functions that we are going to be using throughout the semester. Today, we're going to talk about how to use those parent functions to make different types of graphs. We're going to learn how to use transformations. In general, there are four types of transformations we are going to be talking about today. We have something called a translation, which if you remember the last notes, we know that translation is like a slide. You can slide something up or down or left or right. That's a translation. It's a slide. We're also going to be talking about reflections. A reflection is like we're flipping our graph. A reflection is like a flip. But there are also two more that we're going to go much more in depth with. We've got vertical, stretches, and shrinks. Last notes, we talked about how we can imagine like a piece of gum or taffy, and we're pulling it out to make it taller or pressing it in to make it smaller. But we're also going to discuss horizontal versions of that. Horizontal stretches and shrinks. All four of these transformations are going to be vital because with them, we can basically turn a parent function into just about any other type of function we want. Let's get started. We're going to start here where it says vertical translations. A vertical translation is just a slide up or down. We're sliding our function up or down. And you can see on the graph here that's exactly what's happening. To go from this line to this much more faded line, we're just going up a certain amount. To get from this one to this one, we're just going down a certain amount. Here, it tells us how we can do that in an equation. The graph of y equals f of x plus k is a vertical translation of our parent function. What does that mean? It means if you ever want to move your graph up or down, you can add or subtract a number from the very end of your equation. In fact, adding k to the outputs shifts the graph down when k is less than 0 and up when k is greater than 0. In other words, if I give you a function, we can start to see what that transformation will be. If I gave you the function f of x equals x, but I wanted us to actually transform this a little bit more, we could add something to the output. When we say output, I want to talk a little bit about what that means. Here I have a graph of f of x equals x. It's our normal parent function for a linear equation. With this, we can shift it up or down as we please. So, for instance, let's say I wanted to move my graph up 5. If I wanted to move my graph up 5, what does that mean? It means that every dot along this line should be moved up 5. So for instance, the dot that's right here, we want that to go up to 5. In order to move up 5, we're adding 5 to the y value of every point. So originally, we had 0, 0. What's our new point going to be at? Well, this new point is going to be at 0, 5. We didn't change our input. We didn't change our x values. We changed the output, or what comes out of the equation. It's 5. If we do this for every point on our line, making sure that we move every point up 5, we start to see a new line appear, one that looks like this. And of course, I can connect all those points together to make my new line, my transformed function. So this is why adding or subtracting to the end of an equation will change the line itself. If I moved up 5, what does that mean? It means that our equation, instead of being f of x equals x, is going to be, well, let's use a different letter. Let's use g. G of x equals x plus 5. All we did was we just added 5 at the end of our problem. That's the key thing. When we say that we're adding to the outputs, we mean to the end, or to the whole equation. And it makes sense, too. When we really think about what we're doing here, if we were to make, let's say, a table of values for this graph, if we really think about it, this original graph, y equals x, or f of x equals x, just means that the x and y's are going to be the same. If I plug in, for instance, -1 for x, f of x is also -1, because they're just equal. What I'm literally doing is I'm literally taking these y values and I'm adding 5 to them. That's what it means to move the output by 5. Y is our output. That's all we're doing, is just adding 5 to every output. Okay, let's take a look at this in practice. So the formula goes like this. If f of x equals, let's say, x, all we need to do to change this is to make it so that y equals our original equation, f of x, plus some number k. Let me give you a quick example. Let's say that I have the following equation. Let's let f of x equal 2x plus 1. This is a function for a straight line. You can tell because there's just an x here. There's no x squared or absolute value. It's just an x. But I don't want to stop there. I want to translate this down 7. I want to move this graph down 7. Well, let's look at the equation here and see what we're supposed to do. F of x is 2x plus 1. It's not x this time. Originally we had x. F of x equals 2x plus 1. Our formula tells us that y, our new equation, is going to equal that f of x. So in this case, it would be 2x plus 1. But what are we doing to this equation? Well, like I said, we want to add something to the end, or to the whole equation. To show that we're adding it to the whole thing, I like to put parentheses around the equation. That tells us, hey, I'm adding it to everything with this equation. We'll see what that means in a moment. If I want to go down 7, it tells us that adding k to the outputs shifts the graph down when k is less than 0. In other words, if k is a negative number, it will move down. So we can think of that as adding -7. Moving down 7 is like adding -7. But we know better. We also know that, hey, adding -7, isn't that just the same as -7? So we could also just write it as -7. And this is the way that seems a lot more intuitive. A lot of folks like to remember it this way. Well, now we look at our equation. And we realize something. In this case, when you have a linear equation, if we have 2x plus 1, then -7, there's no reason we can't just write it as this, without the parentheses, because there's nothing special happening with the order here. If we had a squared in the parentheses, or if we had some absolute value stuff, or we're multiplying, then we've got to take care of the parentheses. But over here, there's nothing else to do but get rid of the parentheses. We get rid of them, and we can combine like terms, leaving us with our final equation, y equals 2x minus 6. This is the transformed version of our graph. Similarly, we could do something very, very akin to what we just did with horizontal translations. Here, we talked about a vertical translation, moving something up and down. But for a second, let's say we wanted to move it to the right instead. Let's say I wanted to move this line 5 units to the right, from 0, 0, then moving it 5 units to the right. Well, we know from last time it just means we want to move every point 5 units to the right. So we would get a point here. And what would those coordinates be? Well, if we move it 5 units to the right, what value is changing, our x or our y? It'd be our x value that's changing. Our x value got 5 added to it. So we'll be at 5, 0. Of course, we can do this with every other point on this line and discover that we get a transformed version of our line. Our new line ends up being something like this. If I was to draw it all out, there we go. Oops, marker's fading just a little bit, but I think we get the point. This is the graph that's been moved right 5. Notice how every point here was just moved to the right 5 units. Let's think about that. What does that mean, to move something to the right 5 units? Well, we've got a little bit of a different situation here. Again, here's a table of our original values. We see that if f of x equals x, just like this original equation, then all the x values and all the y values will be identical. But what am I doing here? I'm taking each of these x values and adding 5 to them, right? That's all I'm really doing, is I'm taking all these x values and adding 5 to them. So instead of -2, this will become 3, -2. Instead of -1, this will be 4, -1. Or 5, 0. Or 6, 1. Or 7, 2. We're adding 5 to each of the x values. It's kind of an interesting difference. Before we were adding to our outputs. Here, we're adding to our input. That is how a horizontal shift is done. Be very careful, though, because these horizontal shifts are a little bit counterintuitive. It makes sense for us that when we add k to the end of an equation, it moves up and down. But look what we do here to move it left and right. Y equals f of x minus h. Well, keep in mind, if we added something to the end again, that would be adding to our output, or adding to the end of the problem. We don't want that, because that'll move our graph up and down. We want to add or subtract something from the very beginning of the problem, from our inputs. Subtracting some number h from the inputs shifts the graph left when h is less than 0, and right when h is greater than 0. In other words, let's say y equals f of x is our starting equation, and we want to move this to the left or right. We want to subtract h from the inputs, and it's always going to be subtraction. We're always going to be subtracting h from our inputs. Our input is x. That's our input variable because we're putting numbers into there. We're choosing x. If we're subtracting h from just the inputs, it means that every time I write down x, instead of writing that, I should be writing x minus some number. This one is a little bit trickier to keep in mind because we think to ourselves, why wouldn't we add to the other side? We'll talk about that in just a moment, but let's take a look at an example first. Let's let f of x, once again, equal 2x plus 1. I want us to see the difference. And let's say I want to translate this right, let's go right 3. Why not? Well, according to the problem, all we're doing with this is we're changing every x into x minus h instead. So instead of y equals 2x plus 1, we want it to be x minus some number. Y equals 2 times x minus, if we're moving it right 3, let's take a look at what it says. It moves left when h itself is negative, and right when h itself is positive. I don't care if there's a minus sign here, I just want to know what the actual number h should be. If we want to move it right 3, that number h should be positive 3. So we write down a positive 3, even though there's a negative sign there. That minus sign does not change what our h value should be. The h value is positive if we move it right, the h value is negative if we move it left. It's just that negative sign makes it seem like the opposite. It almost looks like we plugged in negative 3, but that's not the case. We plugged in just an h value of 3. In other words, h equals 3. And then we have our plus 1 at the end. It looks weird, but do you see how all we've done is we've just changed the x here? We didn't minus 3 or add 3 to the end. We changed just the x. Well, let's do some math and figure out what this will look like in a normal equation. We know that when you have something multiplied on the outside, you can distribute that thing. So let's distribute the 2. Y equals 2 times x is 2x. 2 times negative 3 is minus 6. And then we have a plus 1 at the end. Well, this can be simplified. We know this can be simplified into y equals 2x minus 5. This is our equation. Again, we don't care if there's a minus sign there because it's almost always going to be a minus sign. We care about what the h value should be. Real briefly, I want to show you what it might look like when our h value is negative. For instance, here's just an extra little bit of practice. If we wanted to transform the function y equals, let's do 1/2 x minus 6. Why not? That's our original. In fact, sorry, this shouldn't be y, this should be f of x. I apologize. Y is our transformed version. If f of x equals 1/2 x minus 6, and I wanted to transform this by moving it left, let's do it left 4. We've got to consider what that means. Again, we're just taking our f of x and changing it into f of x minus some number, h. So y will be the exact same, except when we write down x, instead of writing down the letter x, we write down x minus some number. Now, if we're going left 4, what do our notes say about moving left? It says we move left when h is less than 0, or h itself is a negative number. So left 4 tells us that our h value should be negative 4. We want to put a negative 4 here after the minus sign. So we plug in negative 4. And we like parentheses because minus and negative always look strange. Well, hang on a second. Minus and negative, is there something we can do there before we start simplifying? We recognize that minus and negative is just the same as plus. So this is 1/2 x plus 4 minus 6. And just like before, we can distribute. 1/2 times x is 1/2 x. 1/2 times 4 is just 2. So our final equation would be y equals 1/2 x plus 2 minus 6, which can be simplified to y equals 1/2 x minus 4. There we go. Remember, moving up and down changes your outputs. So you put it at the end of the equation, or to the whole equation. Moving left and right changes your input, or your x values. So we're going to subtract some number from our x values to make it happen. The reason why we subtract instead of add is because we want our actual x value to change by 5, but for nothing else to change. Putting this minus h there is like compensating for it. For instance, if we started off with f of 0 equals 0, and we want to move it right 5, we still want our actual y value to be staying stationary. So we would have f of 5, we're wanting to plug in 5, still equaling 0. How do we do that? How do we make sure it stays the same and only the x value moves? We do it by subtracting something from both sides. The way we do this is by remembering that f of 5, we want to keep, instead of just x, we want to turn this x minus h into something that will be 0. Our x is going to move over 5, so what could I put here to make sure that this actually turns into 0? Well, minus 5. We have minus h because the x is really what's moving over 5. We want this h value here to make sure that our y values stay the same. All right, everyone, let's flip the page. Now that we've sort of talked in depth about shifts, the next bits will be very, well, not very easy, but it'll be a little bit easier. Let's talk about reflections. Reflections are just another word for flips. But we can flip two different ways. For instance, we can flip something over the y-axis sideways, or we could flip something over the x-axis upside down. For this, I have drawn a little thing that can help us here. This is 1. 1 is perfectly stationary over here in our first quadrant of our plane. Some key points on 1 we might notice are his left eyeball is at 3, 4. The bottom of the circle that Juan's face is right here at 4, 1. Those are just 2 points I chose, but Juan is very geometric. You can see that Juan is very aligned with the grid. The first thing we're doing is we're trying to talk about a reflection in the x-axis. When we say a reflection in something, we mean a reflection over something. Let's take a look. The x-axis is the one that goes from side to side. So we can imagine that Juan is staring into a pool of water here, for instance. Here's the surface of the water, and we want to see what his reflection in the water will look like. I always think of the x-axis as like looking into water. The x-axis is like looking down into water. Well, if he's looking down into the water, what's going to change and what's going to stay the same? 1 is going to be upside down. So if I draw him upside down, we've got to think about what that means. Here, the bottom of his face is originally at the point 4, 1. Is it ever going to change how much left or right it goes? No, it's just going to flip upside down. It's going to go right here. What point is that? Well, the bottom of Juan's face is now going to become the point, just moving this a little bit, is going to become the point for -1. It's still the same amount over. It's still 4 over. It's just down 1 instead of up 1. And of course, we can draw the rest of Juan's face just fine, like so. There's Juan's head. Now we take a look at some of his other features. His eyeball started off in 3, 4. Well, it's never going to shift out of being from 3, 4. It's never going to stop being over 3, but it is now going to be down here, right here. Instead of being at 3, 4, Juan's eyeball is now at 3, negative 4. And his other eyeball is right here, and there's his little smile right here, and there's his tongue right here. This is Juan's reflection, and if I was a better artist, you would see that it should be the exact same. What happened? All we did when we went from one of these to the next is we transformed all of the y values into negatives. 1 became negative 1. 4 became negative 4. The x values all stayed the same. So what's changing? Our inputs or our outputs? If you said the outputs, you're correct, because y values are called outputs. This means to reflect over the x-axis, all we need to keep in mind is, hey, your x values should stay the same. Your outputs, or what you get out of the equation, should flip. They should flip to be negative. Remember what I said about the outputs. So first off, we are multiplying the outputs by negative 1, or just think about it as making them negative. What did I say the outputs were? Last time, I said that outputs were something that you maybe add to the end, or to the whole equation. It's the same here. We want to multiply the whole equation by negative 1. In other words, we want to make the whole equation negative. That will flip the y values, but not the x values. It's a little weird to see, but let's take a look at a different parent function. Let's take a look at the parent function of the absolute value of x. In other words, let's say that f of x equals the absolute value of, what would be a good one to do? Let's do x plus 3 plus 1. Those keen-eyed viewers may recognize, oh, there's a 1 added to the end, so this absolute value graph will be moved up 1, and oh, there's a plus 3 in here, which means it's x minus negative 3, so this will be a shift left. And you would be absolutely spot on. Here is the graph of that absolute value function. F of x equals the absolute value of x plus 3 plus 1. It's shifted left 3 and up 1. That's the function. But we're not talking about shifts right now. We want to do a transformation. We want to flip this over the x-axis by multiplying by negative 1. We want to reflect over the x-axis. Well, what does this mean? Just like 1 last time, we want to change it so that all these points, instead of having a positive x value, have a negative x value. So before this point was at 3, 1, it should now be at 3, negative 1. This point was at negative 2, 2. This should be at negative 2, negative 2. All the points are just being flipped over this line. So when we actually make our new absolute value function, which we talked about last time will be a V shape, it will look something like this. If I was a better artist, it would look even better. But right now, this is what we've got. It looks something like this. It's just flipped. This is the function g of x, I'm just using a different letter here, equals, well, we just want the whole thing to become negative, right? Let's take a look at what that'll look like. If we want the whole thing to become negative, then y, our transform function, will just be, according to our notes, negative f of x. So we want to take our f of x and just put a negative sign in front of it. That's relatively easy to do. We take our negative sign, And since we want this to apply to the entirety of f of x, we put parentheses around to show, hey, it's not just negative absolute value of x plus 3, it's also the 1 becoming negative. And that makes sense because originally we went up 1, now we want it to go down 1. When we distribute this negative to everything inside of the parentheses here, we should see our final result turning into y equals negative absolute value of x plus 3 minus 1. Keep in mind that x plus 3 you can sort of imagine as being in parentheses. We treat absolute value a lot like parentheses. So you could distribute the negative into there. It's not necessary. Just keeping the negative out here shows us, hey, there was a flip that happened. So you could distribute it. I don't recommend it. It's extra work and makes the equation look messier. It would be totally okay to just write the answer as negative x plus 3 minus 1. And there we go. We're not done yet, though. Let's take a look at reflections in the y-axis. So, to reflect in the y-axis, we're doing something very similar, but let's think about it for a second. Let's go back to the drawing of our good friend Juan. Now, we want Juan to reflect over the y-axis, this one that goes up and down. We can almost imagine the y-axis as like a mirror. He's looking in the bathroom mirror, and he's looking at his reflection. It's going to be flipped over in this direction. So what would happen to Juan? Let's take a look at our 2 points that we mentioned before. Our point here was originally 4 to the right and up 1. Are we ever going to change how much up this point is going to be? No, because it's just a reflection over this way. We want this point to stay at the same height, but move left. Instead of moving right 4, we want this point to be left 4. So now if I draw Juan's face, I'm going to try and draw him a little bit better this time. Let's see if I'm succeeding in this. Ooh, I think this is a good one. Bam. Still kind of sucks. But we notice that Juan's face is just moved over left 4. So this point is no longer going to be at 4, 1. It's going to be at negative 4, 1, because this is where the negative x values are. Flipping over the y-axis flips your x values. So instead of being at 3, 4, it's going to be at negative 3, 4. This point becomes negative 3, 4. That's his left eye, which now looks like his right eye because it's a mirror. And of course, we have his sort of winky eye. And of course, we have his smile, beautiful, beautiful smile one. And his tongue is going to be facing over this way. It's completely mirrored. It's the opposite. So, all we did here is we changed our x values to be negative because we're flipping it over the y-axis. Once again, let's take a look at the equation. F of x equals x plus 3, x plus 3 plus 1. To change this graph to be flipped over the y-axis, all we're doing now is we're changing our x values to be negative, right? We're just changing our inputs. Not the outputs. We're only wanting to change our x values or our inputs. So we want to multiply just the letter x in our equation by negative 1, or put the negative in front of just the x. Well, this transformation is actually a little bit easier to deal with, right? To reflect over the y-axis, we just want our original equation, except we're going to put a negative sign in front of the x. So y is the absolute value of not x, but negative x plus 3 plus 1. And that negative is the only thing that changes. It is the only thing that changes. Now, if you really wanted to, you would also be able to write this out in a different way. Let's say you wanted to write this out, y equals absolute value of negative x plus 3 plus 1. Let's say you wanted to write this out without the negatives inside of the absolute value, because that's just bad form generally. If you wanted to write it where the negative is taken out, we learned that if something's in parentheses, you can factor out something from all terms within. If I want to take this negative off the x, I should take it off of everything in the absolute value symbols. So y equals negative absolute value of x minus 3, because positive 3, when you divide by negative 1, is negative 3. This is the same as this equation. And it makes sense when we look at the graph of it as well. Here, in our original graph, we moved left 3, so that's why we have a plus 3. But the graph of y equals negative x minus 3 plus 1, now we have x minus 3 here. Oops, I apologize, y'all. I forgot a simple step. I realized it didn't look right. Keep in mind that we pulled a negative out of an absolute value. So it's really the absolute value of negative 1. I apologize, I totally forgot about that. And what's the absolute value of negative 1? The absolute value of negative 1 is just positive 1. So it's just 1 times x minus 3 plus 1. In other words, it's just going to be x minus 3 plus 1. I knew I was forgetting something in there. I knew that didn't look right. When you pull a negative out of absolute values, you pull anything out of an absolute value, you're pulling out another absolute value. So the graph y equals x minus 3 plus 1, this is just telling us we're moving right 3 and up 1. Our new graph is going to look like this. It's going to be right here. This is the reflection over the y-axis because it is perfectly flipped over that axis. Sorry about the goof with the equation there, everybody. But we got there in the end. This is our transformation. Now, we've got just 2 more types of transformations to talk about. I know this is a bit of a long lesson. Let's start off by talking about, on the next page, vertical stretches and shrinks. We'll save horizontal stretches and shrinks for later. Because we talked about vertical stretches and shrinks before, this one shouldn't be too crazy. All we want to do is we want to either stretch that piece of taffy out in this direction or press it in like a hydraulic press in this direction. That's what a vertical stretch and shrink is. Let's take a look at an example graph. So here, I've got the graph f of x equals x squared. This is one of our parent functions in its base form. Let's say I wanted to vertically stretch it by a factor of 2. What does that mean? It means I want to pull this parabola apart so that it's 2 times taller. How do we do that? Well, let's take a look at some points again. This point right here is the point 1, 1. This point right here is the point 2, 4. If we wanted to make this 2 times taller, what does that mean? Well, what's changing, our x values or our y values? If we're talking about anything up and down, we're talking about our y values. We want our y values to be 2 times taller, right? Well, we're starting here at 0, 0. But let's say I want to make it twice as tall. What y value should go here? Instead of 1, 1, to make it twice as tall, it should be 1, 2, because we multiply our y value by 2. What about our y value here? Well, if we want it to be twice as tall, our 4 should be multiplied by 2. So it should be all the way up here. If we draw the parabola now, we should notice a subtle shift. We notice that our parabola has gotten a little bit skinnier and a little bit taller. This is now the function, I'll use g. G of x equals 2x squared. Because all we did was we multiplied the outputs by 2. So it makes sense that we're just multiplying the entire equation by 2. That's a vertical stretch. So to do a vertical stretch, all we need to do is multiply our outputs by some number. Multiplying the outputs by a stretches the graph vertically when a is bigger than 1. So we wanted a to be bigger than 1. We wanted our stretch to be growing by a factor of 2. It's just multiplying the equation by 2x. By 2. Let's talk about this shrinking as well. Before we do, I want to take a look at the equation that we might see. Again, we're starting with f of x equals x squared. If we wanted to vertically stretch it by a factor of 2, that's a vertical stretch by 2, we're just multiplying the entire equation by 2. Y equals 2 times the entire equation. Our entire equation is x squared. Well, what is 2 times x squared? It's just 2x squared. That's a vertical stretch by a factor of 2. But what if we wanted to shrink it? What if we started with f of x equals x squared and we wanted to do a vertical shrink? Well, let's say we wanted all these points, instead of being twice as tall, to be half as tall. Vertical shrinking, we want it to be as half as tall. Let's see what that might look like on our graph again. If we want all these points to be half as tall, not twice as tall, we're really multiplying our y values not by positive 2, by positive 1/2. Multiplying by 2 would give us all of these values here. If we multiply by 1/2, though, that'll make them half as tall. What might that look like? Well, instead of being at 1, 1, we'd be at 1, 1/2. Actually, this graph is a little bit messy. Give me a second to redraw this. So once again, here's our original graph. This point is at 1, 1. This point is at 2, 4. We want to multiply these y values by 1/2 times 1/2. Well, if we want 1, 1 to be half as tall, that should be the point 1, 1/2. And 2, 4 is going to be 2, 2. We see that our graph transforms by becoming just a little bit wider, like so. Again, I apologize for my drawing skills. It becomes a little wider. It becomes less tall and gets wider. So all we're doing is we're multiplying our whole equation by 1/2, since we're multiplying the output by 1/2, or the y values. All we're doing is we're changing it so our y values are 1/2 of what we would normally get. So our equation is just y equals 1/2 of x squared. To do a vertical shrink, to shrink the graph vertically, our a value should be a fraction, or in between 0 and 1. Last but not least, I want to talk about this. I know it bleeds through the paper a little bit, so I apologize, but I want us to talk about horizontal stretches and shrinks, because they are slightly different, but it makes a big difference. Let's go back to our graphs. So here, we've got our graph, once again, of just f of x just normal as it is. This is y equals, or sorry, f of x equals x squared, I should say. And once again, we've got our points. We've got our points here, 1, 1, and 2, 4. I want to start off by stretching this graph horizontally. It's like we're taking the ends of these parabolas and just pulling them apart horizontally now. That's what a stretch is. Well, stretching it horizontally, what's affected? Are we affecting the y values? No, those should stay at exactly the same height. What we're doing is we're changing the x values to be wider. Let's say I wanted to do a horizontal stretch by a factor of 2, meaning I want these to be 2 times as wide. What are we multiplying by 2? We're multiplying our inputs by 2. So instead of 1, 1, we should put a point at 2, 1. And instead of 2, 4, we should put a point at 2 times 2 is 4. We should put a point at 4, 4. Our parabola is going to become twice as wide. So it's going to look something more like this. There we go. And, oops. There we are. That's twice as wide because all of our x values got shifted to be twice as far away. Well, let's think about it again. We've talked a lot about inputs and outputs. Let's see how this reflects in an equation. Again, we're doing a horizontal stretch, so it says here that this is going to impact our inputs. We are going to be multiplying the inputs by some number. We're multiplying our inputs by some number now. In other words, if we start off with y equals f of x, the transformation is y equals f of some number times x. We're just changing it so that the x value, instead of being by itself, now has a number multiplying it. So let's start off with f of x equals x squared once again. If I wanted to horizontal stretch by a factor of 2, we really have to think about what this means for the graph. If we're horizontally stretching by a factor of 2, sure, we are getting wider by 2. But what does this graph look more like? Does it look like what we did when we multiplied by positive 2? No, multiplying by a number greater than 1 made it a little skinnier. It looks more like this when we multiplied it by 1/2. This is the weird part, and this is why I saved horizontal stretches for last. For horizontal stretches and shrinks, it's sort of the opposite of what you think it should be. If we want to horizontally stretch something by 2, we want to multiply the x by 1/2. I know, super strange. But it makes sense. If we want to stretch this graph horizontally, when these are our values, let's see what we get. We don't want our y values, our outputs, to be bigger. We want them to be smaller. We want the y values to stick around while the x values are what's changing. Just like how, when we did the shifting left and right, remember how we had a minus here to compensate? It's the same deal. Instead of multiplying by 2 to stretch it by a factor of 2, we're going to multiply by 1/2. It's the opposite of what we think. So y equals, our f of x is going to stick around, except we want our x to be multiplied by some number. That number in this case is 1/2. 1/2 x then squared. Remember, the squared is something that happens to the x, we want this 1/2 to apply first. But hang on a second. We might recognize that this 2 can be distributed to simplify our equation. If we distribute the 2, what is 1/2 squared? 1/2 squared is 1 squared over 2 squared, which is 1/4. And we have our x squared. This is something very critical. When we are horizontally stretching by a factor of 2, we're vertically shrinking by twice as much when it's a parabola. It's sort of a unique little trick. Well, let's take a look and see if we can do the same thing for horizontal shrinks too. Let's say we once again have the same graph of f of x equals x squared. Let's say we want to shrink this by 1/2. We want to make it so that these points are twice as close together, horizontally shrinking it. Well, it makes sense that instead of an x value of 1, we multiply that by 1/2. Instead of an x value of 2, we can multiply that by 1/2. Our new points are going to be 1/2, 1 and 1, 4. Because that'll be a horizontal, that'll be a horizontal shrink by a factor of 2. It's going to look something like this. This is our new parabola. It's horizontally shrunk, but it looks like a vertical stretch. It looks just like this. Well, maybe not just like this. You can see that it's way more shrunk vertically. Let's take a look and see what it looks like on the equations. Once again, we are multiplying our inputs anytime we do something horizontal. Horizontal means x. So if we start off with f of x equals x squared, and we want to horizontally shrink it by 1/2. Horizontal shrink by 1/2. We can do so by, just like before, we do sort of the opposite, multiplying by 2. Multiplying our input by 2. So y equals 2x squared. But hang on a second, we can distribute that squared if we would like to, and we do. We end up with y equals 4x squared, because 2 squared is 4, x squared is just x squared. This is our horizontal shrink to be half as wide. Weird business, right? That's why I say that vertical stretches are like horizontal shrinks, and horizontal shrinks are like vertical stretches. They're similar, but not quite the exact same. All right, everybody. That is the end of our notes for today. Make sure you get some practice with these transformations, because next time we're going to talk about how these apply to parabolas specifically. With that said, have a fantastic rest of your day.